button. And we're gonna make a move. All right. So we talked about let me see what we stopped on Friday. We stopped at the SN1, and we talked about the rate, the fact that it's stepwise, and we also talked about the solvent and how the solvent can solvate the leaving group to help speed the reaction up. All right, so let's look at another SN1 example. And here, since we have already gone through the mechanism, I want to just talk about or predict the product. Right, so for this example here, what is the product? And then we're going to go through and talk about the other components of that reaction too. So what's the product? What would the product?
We already did the products, I think, did we?
We did the top.
Maybe I did them.
We didn't do the second.
Okay.
Yeah, we did this one. What's going on with this thing? But we didn't do the bottom one.
Right.
So what's the nucleophile here?
The OCH3.
So this is my nucleophile. Makes this the substrate. And then the chlorine is the leaving group. And then the solvent is it protic or aprotic?
Protic.
You sounded scared. Right, it's protic. All alcohols are protic. What does that word mean again, protic?
It can donate a hydrogen.
Yeah, it can donate H plus. Right, that's what we call a H plus a proton, right? And so a protic solvent is able to donate a proton. That's all it means. So any alcohol, you see the OH group right here, any alcohol is going to be protic. All acids are protic. And then carboxylic acids are also protic. All right. So what would the product be? If chlorine is my leaving group and the methoxy group is my nucleophile, what would the product be?
The chlorine would be by itself, and the OCH3 would connect to this little,
the little thing right there.
Yep.
You mean the carbon?
Yes.
So like this, right? Is that right?
Yes, sir.
Let me put. I don't know why my pen is not working. I gotta order another one. All right. So so for the SN1, I think the key takeaway is that it is stepwise and it goes through a carbocation intermediate, which I showed you on Friday. And then the rate, we said was a one-term rate law. We said it was a one-term rate law, and it only depended on the substrate. Right, so the rate is K. K times the concentration of the substrate. All right, let's jump down to the E2. All right, So elimination is, again, we're talking about the formation of a pi bond in the product. So here's some of the factors that favor E2, right? Tertiary carbons, tertiary or secondary. It can happen on a primary too. That's not the issue, but it favors tertiary carbons because the alkene that you get from a tertiary carbon is going to be more substituted. And then also you need a base. Right? You need a strong base for that to happen. All right. And it also follows Zaitse's rule, which we're going to talk about when we do the actual example. All right. So I want to draw the products in first up here. I'm not going to do the top example. I'm going to do the bottom example because that one is more. We can get into more detail with that. So when you see KOH, the K is positive, the OH is negative, right? So this is a really good base, and the OH is the part of the base that's going to do proton transfer, right? All right, so it's a couple of things about this E2 that we're going to talk about. So I want to draw the products first, then we're going to come back and talk about the different features of the E2. So here's one. Here's going to be one of my products. And then my other product is going to be here. All right. So I'm going to get two products in this particular case. And the reason is because when elimination happens, it has a specific pathway that it's going to follow. All right. So let's go over here. The first key to understanding elimination is to locate the leaving group. What are you looking for when you're thinking about finding the leaving group? I think we talked about this already.
The rate determining step?
No, I mean just in general. When you think of an atom or a functional group being a leaving group, what are you looking for? You're looking for some polarity, number one. Remember we talked about that when we were doing those substitutions and that arrow pushing. You're looking for some polarity, and you're also looking for a dipole, like some type of dipole. So if you look at this molecule, the most polarized bond in there is the carbon iodine bond. So that's more than likely that's going to be your leaving group. So then for elimination, once you find the leaving group, the next thing that you need to do is identify what's called the alpha protons, because these hydrogens that are on the carbons adjacent to the leaving group, those are the ones that get pulled off. Right, so those are the hydrogens, and we call them alpha hydrogens. Right, they're adjacent to your leaving group. And when the elimination happens, those are the hydrogens that are going to do proton transfer with the base. All right. So let's see how we formed. We're going to call this A. That's A, and that's B. So how do we get to A? What does it look like happen? Where's the double bond located? Right, it's right here, isn't it? Is that right?
Yes.
All right, so that means that this is the hydrogen that we have to remove to get to A, right here. Right, so let's see how this happens, and then we're going to talk about the other parts of the E2 mechanism. Right, so the OH is going to come in. I'm going to zoom in so I can make sure my arrows look right. The OH is going to come in here, not with a highlighter though. It's going to come in here like this. Boom. Hit that hydrogen. These electrons from the CH bond are going to go here. And then let me erase all this highlighted stuff since it's the same color. And then this pair of electrons is going here with the leaving group. All right. So what can you say about this mechanism if all this stuff is happening all at the same time?
It's concerted.
Concerted. It's very good. It's a concerted mechanism. If I can spell, I'll be all right. Right. It's a concerted mechanism. That means that everything is simultaneous. All right. And so for this particular side, for this side, your double bond is going to end up here. Right. And you can see in the product, that's exactly what we get. We get a double bond at that position. Because remember, anytime you eliminate, you are forming a pi bond. So you also have to lose something, right? What do we lose here?
The iodine.
Okay, you lost iodine, good. And you also lost hydrogen, is that right? Because the hydrogen gets pulled off by the hydroxyl group. So let me show you over here. So you're going to get water. I'm going to write it out as HOH. And the iodine leaves, so it's here and it's floating and it's negative. So that's where potassium is going. Are y'all following that? So anytime you have a counter ion that's positive, it's normally going to find your leaving group somewhere, right? You're on the other side of the reaction arrow. So Ki ends up, well, potassium and iodine end up together because iodine is negative. And then obviously the OH hydroxyl anion, the hydroxide pulls off hydrogen, so that becomes water. Are y'all following that?
Yeah.
All right. Any questions? Go ahead and ask them. There's no wrong questions, bad questions, dumb questions. No such thing.
Where did you get the how do you say it? Iodine from?
Iodine?
Yeah, iodine.
That's all right. It's right here, right? That's my leaving group. You see it right there? It may be hard to see because it's not an old-fashioned eye.
Oh, I was wondering why like it was bolded and all that. Okay.
Yeah. Let me put some little handlebars on there. Like I'm gonna make it a kindergarten eye. There we go.
All right. Thank
How
you.
you see it?
Yeah.
All right. Yeah. It's the font that I was using in my drawing software. That's why it looks like that. But all right. Okay, so I think we're okay with that. But there's also a set of hydrogens on the other side that are susceptible to proton transfer too with this base, right? So let's see if we can put the arrows in for that one. I'm just going to change the color, right? So this pair of electrons is coming here, boom, like that. I'm going to push this pair of electrons here. That's where those are going to be the electrons to form my pi bond. And then I'm going to lose my leaving group. Again, it's concerted. It all happens at once, and the hot carbon hydrogen bond, those are the electrons that are going to be used to make my pi bond here. right? And I know somebody's thinking this, but you're scared to ask it. Somebody's thinking, well, can I do both sides at the same time? No, you cannot, right? You either gonna do one side or the other because you're gonna get both products. Are we okay with that? All right. So again, in order for E2 to happen, you need a strong base present, right? So the fact that it is concerted, what is that? Which one of the mechanisms that we've already studied is this related to? Or not, I don't want to say similar because it's not the same mechanism, but it's related to which one? What do you think?
Is it as
It's kind of related to the SN2 in the sense that it's concerted. Am I right? And so even if you notice here, we call it an E2 elimination, right? So what does the 2 stand for again? Anybody?
Biomolecular.
Biomolecular. So that means that it is what? How do I write the rate law for that? See, we already have been exposed to this with the SN2. And the 2 in the E2 kind of gives away that it is a biomolecular reaction. So the rate is going to be K times the concentration of the substrate times the concentration of the base. All right, so there's a difference here. Instead of a nucleophile, it's the base concentration that matters, right? And not the nucleophile concentration. All right. Yes, no, maybe. Can you see where the 2 products are going to come from?
Yes, sir.
Yeah.
All right. And again, the rate is going to be dependent on both the base and the substrate. And then and another thing too is that the solvent is aprotic. And I did update this handout in Blackboard too, by the way. I changed it so you'll have the solvent list and the leaving group list, which we're going to talk about in a minute. I'm going to bring that up too. But I did update it. So it's an aprotic solvent. Why would you think that an aprotic solvent is necessary for the E2? Think
so
about
it doesn't protonate your base,
who was that?
Maria?
Come on now. God, on a Monday. You're right. You don't want your base to get protonated. That's exactly right. And so if you have a protic solvent around your base is just going to exchange protons with it, and the reaction is just going to go to crap. So you have to do it in an aprotic solvent to preserve your base. Thank you for saying that. That's you all right with me. I don't care what.
Thank you.
Yeah, it's so the base has to be preserved, and so the way you preserve it is by not putting a protic solvent around it. Sorry about that. I don't know what's happening with my screen. Or maybe that's just on my end. All right, good job. Yeah, so you have to use an aprotic solvent, and again, the rate is 2 term and second order overall. And then another piece of information about the E2 is that it follows what we call Zaitse's rule, right? So Zaitse's rule tells us that the more substituted alkene is going to be favored. We're going to talk about alkene substitution now. right? So Zaytzel's rule says that the elimination is going to favor the more substituted alkene. So I'm going to stick a page in here so we can talk about alkene substitution without trying to jumble it all into one place. All right. So let me put a heading up here. Right, so this is the basic framework for an alkene, right? You just have two carbons double bonded together. Now, if you look at that, you can actually add carbons to either side, right? If I don't have any carbons, I have all hydrogens, this alkene is unsubstituted. Right, it's unsubstituted. So I have no no carbons attached to it, right? If I take that alkene and I'm gonna copy it so I don't have to keep drawing it. But this time I put one carbon on it. Right? This type of alkene right here with one carbon bonded to it is what we call monosubstituted. You can probably see where this is going, right? I put two carbons on. Let's see if I can paste it again. Add another page too. All right, so I'm gonna put one more carbon on there. Right? This would be an example of what we call disubstituted, because it has two carbons. You see that? So two carbons. Not too bad. It's disubstituted, one carbon, monosubstituted. You can see where this is going, hopefully. I don't know why that's still showing, but that's all right. All right, if I stick on 3 carbons, what do you think? It's a progression, right? We go mono, di, and then tri-substituted. Is that can you see that other stuff on the screen, or is it only the alkene? It looks like some.
Yeah, we can see the other stuff.
You can. All right, hold on. Let me see if I can erase that. It won't erase. Hold up. There we go. It's technology, man. I don't know. All right. So that's tri-substituted. And then what do you think the next type of substitution pattern is? Right. That's when I have all carbons attached to it, right? And this would be considered tetra substituted. Right? And the thing about it is the more carbons you add, the more stable the alkene becomes. Because think about it, the alkene carbons are sp2. So they're a little bit more electronegative. And so the more electron density you put around them, the more stable they become, right? Because you get that same phenomenon like we talked about with the carbocations. You get these carbon-carbon sigma bonds kind of donating electron density towards the sp2 carbons, right? So the more carbons you put around the alkene, the more stable it becomes. All right, so we go back up to our example right here. What is the, I'm gonna redraw this bottom one right quick. What's the substitution pattern for A? Is it mono substituted, di substituted, tri substituted? What is it? You got a carbon attached to it here, here, and here. What do you think? And you only have one hydrogen on it, which would be here.
Tri.
Huh?
Tri substitute.
Try. Yeah. Come on. Don't be, nervous. You don't lose points by saying something that's wrong, and you don't lose nothing. It's either gonna be right or wrong, and if it's wrong, we're gonna correct it. So just say it. So try substitute. Good. What about the one underneath it? You got a carbon here, and you got a carbon here. Is that right? So you got two carbons attached to the alkene, to the double bond. What substitution pattern is that?
Di substitute.
Thank you. Di substitute. So according to Zayzev's rule, the more substituted alkene is going to be more favored because it's more stable. So if we apply Zayzev's rule to this example, which one of these is going to be favored?
The tri.
Try.
Exactly. Right. Let me zoom out a little bit. So A is going to be favored. Right. Well, we call A, according to, like, when you're looking at a competitive process where you got the potential for more than one product, A, if it's favored, we're going to call it a major product. That makes the di-substituted product the minor product. All right, so you have major product, a minor product. And that is, again, just like we talked about with the radicals, it's a function of what we call a product distribution. Right? You got competitive processes where you make more than one product, you're always going to have one of those products that's favored. But what makes it favored is going to be dependent on the type of reaction you're doing. All right, any questions about this so far? So again, the rate law is second order. Zayt's rule says that the major product is going to be the one that's more substituted. The mechanism is concerted. You have to do it in an aprotic solvent, and you need a strong base. Let me give you, I don't remember in that elimination video whether or not it gave you examples of good bases. I think it did. I can give you a quick list of ones you'll see. Add a page there. All right, so let me do that, and then we're gonna do another example. All right, so your amines These are excellent bases. Alkoxide bases like, I'll write this down right here. Normally you'll see this with a potassium, and you'll see it abbreviated as K. You'll see it abbreviated as KO, lowercase t, BU. That's because of this group right here. This, the group that's attached to oxygen. This is a tertiary butyl group. And so the abbreviation for that is a lowercase t and then uppercase BU. That's how. So the KOT bu, we call it, is potassium tert butoxide, ERT. So potassium tert butoxide. That's another really good base. The alkoxide bases they become, the more bulky they are, the better they are as bases. The smaller they are, they become more nucleophilic and less basic. But for the purposes of what we're talking about with the elimination, we're gonna you'll see the potassium tert butoxide listed as a base. So if you see that, or if you see this, then you'll know that you're dealing with a strong base that you can use for elimination. Another base that you'll see sometimes is a base DBU, and then DBN. I think DBU is diazo bicycloundecane, and DBN is diazo bicyclonone. Let me pull it up right quick. That way you can see what the structure. I know the structure is in the video though that I sent out. Yeah, so DBU is diazo bicyclo undeck 7-ene. I said ane earlier. It's ene because of this little double bond that's in. Let me pull it up. So this is what the structure of DBU is. So each one of those nitrogens is going to have a lone pair, and that's where your basicity comes from. The nitrogen lone pairs are what do the proton transfer, right? So that's DBU, and then DBN. Let me see if I can find that. Yeah. So this is DBN. It's very similar, just 2 less carbons, because undecane is 11 carbons, and nonane is 9 carbons. But we're gonna talk about that another time. All right. So this is another really good base, and if you see the acronym for it, DBU or DBN, then you'll know that is a base, and it'll give you a clue as to whether or not you're doing E2 or E1 or SN2 or SN1. Anytime you see a base present, more than likely you're going to be doing E2 elimination. All right. Any questions about anything? Let me put the OH hydroxide ion on here too, even though a lot of times you'll see it as, you'll see that a hydroxide used as both a nucleophile and a base. So, but KOH and sodium hydroxide are both really good bases. All right. Any questions about anything about the E2 mechanism, the arrows, we're gonna work some examples on Wednesday because I think I added a page in the handout that's on Blackboard. I added a page with some really good problems on it. So we're gonna work through some of those on Wednesday. All right. No questions about anything.
Can you scroll down actually to
The basis.
yeah. Is there a way you can get all of, well, no, actually go back up.
Back to here.
Yeah. Is there a way you can get all of them in one? Nice.
I'll scroll up to so you can just get the ones that are substituted.
Thank you.
Mm-hmm. All right. All right, just let me know when you're done, and then we're gonna touch on the E1, and we'll probably end with that, finish with that, the E1.
Oh, I'm done.
Okay. All right. So let's go up and talk about this E1. I want to move this because I don't want to run out of room. Yeah, I'll move it because I know me. Cut that out. So what are you thinking about the E1 automatically? The fact that, what do you think that one means?
Unimolecular.
Unimolecular, right? And so the fact that it's unimolecular gives you a clue about the mechanism, and it gives you a clue about the rate law immediately, right? So for the E1, let's switch pens right quick. All right. Just like the SN1, the rate is K times the concentration of the substrate. Just like the SN1, the rate determining step is the loss of leaving group, right? Just like the SN1, you get a carbocation intermediate. Right, just like the SN1 is stepwise. Right, so it has all that in common with the SN1. The rate law, the rate determining step, the intermediate, the type of mechanism being stepwise. And then, so unlike the E2, I missed something on E2. I need to go back and talk about it. Or maybe, yeah, I'll just leave it. So you don't need a base. And then I won't leave it. I can't leave it hanging like that. You don't need a base, and there's no specific geometry. I'm gonna come back to that and talk about that. Right. So let me do it now. So for the E2, there's a geometry that you have to adhere to in order for elimination to happen. So let me give you a rough, quick and dirty crash course into what we call a Newman projection. Well, before I do that though, let me show you this. All right. So if I eliminate it from here, where, man, that's going to bleed off. But this is my leaving group, and this is my alpha hydrogen. Right? When you do an elimination, an E2 elimination, these things have to be opposite. So the hydrogen and the leaving group have to be on opposite sides of one another. Right? And keep in mind, these are two, this is a carbon, and that's a carbon, right? So the leaving group and the hydrogen have to be on opposite sides of the same plane. So we say that they have to be anti meaning opposite, and then peri, same, and then plane. Periplanar. Anti-periplanar. That's a requirement for E2. If your leaving group and that alpha hydrogen cannot get on opposite sides of one another, and that's possible through rotating around the carbon-carbon bonds. We haven't talked about Newman projections yet, but we will. We actually are gonna have time to get to that, which is a blessing. So if the leaving group and the hydrogen next door to it, on the carbon next door to it, can't get into this conformation, then the elimination can't happen. So this is for E2. Right? It has to be anti-periplanar. Right? And for E1, it doesn't matter because it goes through a carbocation. So the geometry is not necessary. But for E2, you have to go through this specific type of geometry, this anti-periplanar conformation. All right. So for E1, again, no base. So it's different from E2 in that respect. And then no geometry, no geometric requirement, which is also makes it different from E2. So let's look at the reaction that I pulled down, and let's look at let's see how it happens. Go through the mechanism. All right. I don't know why this is not doing what I'm telling it to do, but that's okay. All right. So, excuse me. Let me draw the product, and then we're going to talk about the mechanism. So here's the product. This is a classic example of an E1 elimination. It's a dehydration reaction. All right, so it's a dehydration, meaning that you lose water. Right, so you can see in the product, you get water, and then you also have the acid that you started with, right, regenerated. Right, so that acid is acting as a catalyst, right? And it's not going to get consumed. It's only going to facilitate the reaction. So let me put that in here. Right, so the acid is acting like a catalyst. It's not going to get used up. So every time you go through the mechanism from start to finish, you're going to regenerate the acid, and then that acid can go back and you start over on another mole of alcohol, right? So let's look at how this happens, and then we'll discuss like some of the different features of it along the way. So here's my starting material, my alcohol. I'm gonna put my H on this side. And I'm reacting that with sulfuric acid. So this is the structure for sulfuric acid. All right. So first step is proton transfer, right? And I'm gonna talk about this. I'm gonna give you another piece of information here too. So the proton transfer is gonna give me an intermediate that looks like this. So it's O, H, H, and that oxygen is positive, right? So this is an intermediate. And the reason why this is necessary is because OH by itself is a bad leaving group. It's a very bad leaving group. It doesn't leave spontaneously like you would expect if you're doing a SN1 or whatever, like a unimolecular reaction. You expect the leaving group to leave spontaneously, and here it doesn't, because it's not a good leaving group. I'm gonna show you. I have a list in here of how to determine whether a leaving group is good or bad. And let me show you that right quick. So this list right here, it gives you a sense of how to judge a leaving group, right? And it goes back to what we learned when we did pKa and hires, right? And how conjugate bases are stabilized, right? So your leaving group is going to be based on the pKa of its conjugate acid. All right. So if the leaving group is iodine, then the pKa of the conjugate acid, which would be HI, is -10. That means that iodine is really stable conjugate base, because that's what the leaving group basically is. It's like a conjugate base, right? It has a charge. It picked up a pair of electrons, and it's just kind of hanging, you know. And so you can basically you can judge it based on you can treat it like a conjugate base, and if you know the pKa of its conjugate acid, then that'll tell you whether or not that leaving group is good or bad, right? So we go down here to hydroxyl. Notice it's all the way down at the bottom, right? And it's got so the hydroxyl group as a leaving group, the conjugate acid of that is water, right? And look at the pKa. It's 15.7, right? That's not horrible, but that's not a good leaving group. So that's why we have to add that acid in to catalyze that reaction, because you want to get that OH to leave. And one of the best ways to get OH to leave as a leaving group is to protonate it and turn it into what we call a hydronium ion. So let's go back up to here. Right, so now you got this hydronium ion intermediate. I'm gonna put the name down there because that's important. And now that's ready to leave, right? Right, now that's ready to leave. So here's where you'll see the loss of your leaving group. The first step in this E1 dehydration is not the loss of the leaving group. It's the proton transfer, and then you'll see the loss of your leaving group, right? And that's going to give you your carbocation intermediate. So now that carbon here has a plus charge, and then it's plus H2O. All right. Questions about that? All right. So the next step is the elimination step. But the question is, like, what's going to facilitate the elimination, right? Water can also act as, it can be an acid or a base, right? Remember that from CHEM. It can be an acid or a base. Or if you look over here, right, when you did that proton transfer, you also, right, when you did the proton transfer, you also get a conjugate base from sulfuric acid, right, which is, let me see if I can copy it so I don't have to redraw the whole thing. I know that's cheating, but it's okay. Never mind. Just draw it out. So you get the conjugate base from that too. I'm gonna draw it over here. So it would be S O minus, right? Because you lost a proton from there. And so either the water or the conjugate base can do the elimination, right? I like to use the conjugate base because it eliminates another step. Because if I use the water, then I got to show another step showing a proton transfer between the conjugate base and H3O plus, and I don't want to have to do that. So I'm going to use the conjugate base to do the elimination. So I got a plus charge here. Keep in mind, I got 2 hydrogens here. And then plus never mind. All right, so now this can come in, boom, and then take that proton from there and do your elimination, right? And that's going to give you your product, which looks like this. Plus the acid regenerated plus water. All right. So with the E1, let me change the color on this plus chart. So when you look, if you look back at the notes, you don't get confused. All right. So with the E1, again, it has a lot of the same characteristics as the SN1, but then it differs from E2 in that it goes through, it's stepwise, so it goes through a carbocation, but you also don't need an outside base, right? Keep in mind, if you look at what we started with, we added acid, not base, right? So you don't need an external base, and there's no geometry, no requirement for anti-periplanar or any of that. All right, we're gonna stop right here, and we're gonna pick up on Wednesday, just working problems and doing examples. And I'll keep adding in information where it's appropriate when we work through those problems. Any questions about anything?
I have a question.
Come on.
You know, like the charts you were going through, like to basically solve the problems. Where is that on Blackboard? I was trying to find it, like the different charts.
You
that
talking
roll-
about the leaving, what I just showed you with the leaving group?
Yeah. Mm-hmm.
It's in the handout in module 3.
Yeah, it's in the third module
Third module. Let me pull it up right quick.
under assignment.
Yeah, third module and assignments. I updated it. I think I updated it Saturday, Friday or Saturday, one of them.
Okay.
Yeah, but it's there.
Thank you.
hmm Any other questions? All right, I'm going to stop the recording.